All right, welcome to our Chapter 39 discussion. This week I want to start off talking about stairs by looking at a SketchUp model, kind of like we did with the wall section. And just like with our demonstration of the wall section, I want to take a look at the individual components, both in 3D and in projected view, just so we're all familiar kind of with what we're drawing when we start doing the wall section actual design work. I should say stair section actual design work. So we've talked a little bit about stair sections in the past, and so some of this is just going to be a review, but go ahead and just take a look at all the individual components you see here as we rotate around this model and see if you can recognize some of those components that we've really mostly only seen in section view before. And hopefully the 3D view gives a little bit more clarity as to what it is exactly that we're drawing, all these individual components. So you'll recall that the diagonal members, those are going to be your stringers. And typically those are going to be cut from a 2x material. Oftentimes it's going to be a 2x12 because they have the maximum depth or width of the board this way. And remember that when we look at a stair straight on, you can kind of picture that 2x12 running down parallel to the back side is an imaginary line running across from this point right here to all of the other points. And that represents essentially where the original other edge of that 2x12 was. So we can imagine that the distance from this point right here down perpendicular to the back side of the stringer is going to be the width of a 2x12, 11¼ inches. So on this particular model we have 3 stringers, as you can see, and they've all been sort of cut out already to accommodate the tread board, which is on top here. That's the part we walk on. It's got a little nosing, a little overhang right there, and then behind and under the tread is the riser board. Moving up to the top, you can see that there's a small board kind of hanging down from this header. It's a little bit hard to see, but it's basically attached to the header back here, and it's hanging down to provide positive attachment for the stringer. The main structural part of the stringer sort of runs in this area right here. And so this part of the board, if you follow the grain up, is really what needs to be attached to something for this to not fail. Taking a look next down at the bottom of the stair, we have what's called a kicker. This is a board that's usually either notched in or attached in some way to the stringers, and then it's also attached to the floor that it rests on. And that's basically just preventing the bottom of these stairs from kicking out should there be a failure with the connection point up at the top. The components we're not seeing in this view is a handrail, which we know is necessary at least on one side of a stairway. And we also don't see a landing anywhere at the midpoint of this stair. Because it's a straight run stair, oftentimes we don't need a landing. Now the exception to that, and this is kind of a number you might want to keep in the back of your mind, is 12 feet above the first floor, the lowest floor, we are required to put a landing in if the stairs don't reach the next level by that point. So a 12-foot vertical rise per run of stairs is the maximum that code will allow before you have to put a landing, which is basically just a resting spot for folks that are more elderly or disabled. Putting an intermediate landing at the 12-foot mark also limits the number of stairs that a person can fall down, and it's still a whole lot of stairs and you can still get hurt, but imagine an unlimited number of stairs without a landing. That could be a pretty disastrous slip and fall. Most residential stairs don't require that midpoint landing because the floor-to-floor distance is less than 12 feet. Up at the floor system itself, you can see that the stair opening is wrapped by, we have joists on the sides, and then we have headers sort of coming in and blocking off those joists that would have otherwise passed through that opening. Typically all of those members are doubled. The headers are doubled, and usually the joists that hold up the headers are also doubled. These ones are not, just to be clear. This model isn't completely accurate, but in most cases this joist right here and this joist right here all the way through would be a double joist. Okay, so I think that's good enough for the introduction on this lesson. Let's go ahead and jump into the PowerPoint. So chapter 39, if you haven't figured out already, deals with stair construction and layout. So the first slide is just kind of showing an example of a stair. This would be maybe a good one to start with because it shows the stringers without anything else attached to it. And you can just kind of see how those stringers can go up to and attach to whatever that floor structure is up there. And then it's going to come down, and typically, you can't really see it very well, but it's typically the bottom of that stringer is going to either rest on a floor or a landing, or it's going to be tied in with a hanger or some other method. In this case, you can see that the stringer is actually nailed to a post in this example. Now presumably, and we can't see it, but these other two stringers are either nailed to something similar or they're resting on a platform. Here's another example of a stair. This one obviously is a U-shaped stair. Some people call them different things, but I've always known it as a U-shaped because in plan view it's basically creating a U, right? The path of travel is basically in the shape of the letter U. See if you can notice a difference between this stair and the one we were just looking at in terms of its structure. One of the things you can see right away is that there's not a central stringer. There's no middle stringer on this one, at least not that we can see in this view. The other thing that jumps out at you is that the stringers are not notched. So the stringers are actually kept whole in this case. It's the whole board, and the treads and the risers actually fit between the stringers. So that means there has to be some type of bracket system on the underside of the stringer, right, to hold up and to support the connection between the treads, risers, and the stringers themselves. So hopefully looking at a few examples will open your eyes to the fact that not all stairs are the same. In fact, stairs can vary quite widely. We're going to see another few examples in this PowerPoint that are, some examples are pretty exotic, right? In all cases, though, we need to be code compliant with our stairs, regardless of the materials or the methods that we're using. Here's a good example of a finished stair. So this would be a type of stair where we wouldn't enclose the stairway with a wall system and hide it. And when we don't hide the stairs by putting a wall up, it typically means that we're going to have to finish those stairs with a lot more finished carpentry detail than we otherwise would. Just look at the side of this stringer, for example. Look at the side of the treads. The detail that goes into all of that work is considerably more than if you were just going to run, say, particle board treads inside a stairwell and then cover it all up with carpeting or something, right? So this is all intended to be left exposed, and this stairway isn't finished. Obviously, they're going to have to do some sort of like varnish or stain or both on this stair before it would be considered done. Here's another example of a finished stair. This one is quite a bit more exotic, a little bit fancier, right? Probably more expensive too. So we're mixing wood with painted wood in this case to kind of give a lot of contrast and really make these stairs sort of jump out as a feature of the structure. Here's another set of stairs, and this one, for obvious reasons, is not code compliant, right? So we don't have a guardrail on the open side, and we don't even have a handrail on this set of stairs. But it's in this PowerPoint just to sort of demonstrate that stairs vary widely. There are lots and lots of different ideas people have for stairs, and there are certainly far more than what I've shown you here. There's all sorts of different stair types. This is just a small sample, but it kind of gets your mind going in the area that it needs to go, which is the part we're concerned with is the part we're walking on and the primary components that code has something to say about. So we're going to be talking a little bit about the different stair shapes. We've seen a few different stair materials and styles, but the shapes of stairs are really what define them. And here are a few. Right? So one of them is the straight run stair layout, and that's just where we go in one direction, up or down. And so that one is actually the simplest and most economical to build in most cases. The next one is the open stair layout. And open stair layouts basically are talking about the space between the treads. Are we going to be able to see through those down to the space below, or is it just kind of left open? And then L and U-shaped stair layouts, those are referring to the shape of the stairs, just like straight run, as it appears in a plan view. So if we're looking down from above, does it turn one direction or the other? That would be an L shape, and a U shape would make a full U-turn and go up the opposite direction. Here's a review of some basic terms. Take a minute and make sure that you're familiar with every one of those. If not, just make sure that you look it up. These are all words that you should know. Here's an example from the book that shows the various components of a stairway. Again, expanding your familiarity with the terms we're going to be using over the next couple weeks. We're also going to be talking a fair amount about code. Code does have a lot to say about stairs. And the reason, of course, is similar to all of the other reasons code has something to say about a building. It's to increase safety. And stairs, for obvious reasons, is one of the most hazardous places in a house, right, or a building. So we want to make sure that they're not too steep, that we have plenty to hang on to when we're going up and down, and that the shapes of the stairs don't cause trip and fall hazards. So a straight run stair, that's the most basic, most simple type of stair to build, also the most economical, and it tends to use the least amount of floor space on a floor plan. This is an example of a couple of, these are stacked, and this is common strategy when we have a straight run stair that has to span more than 2 floors. We're typically going to stack the stairs one over the top of the other. That's the most efficient use of that floor space because we're already giving up floor space for the stair. We don't want to increase that by putting a whole nother stair someplace else in the house. So typically this is a strategy that we're going to follow. But the straight run stair just runs in a straight line from one level up to the next. And obviously this particular stair you'd have to walk around to the other landing and then head up the rest of the way to the 3rd level. You really can ignore the steps that they talk about in the book for drawing. This is really a throwback to when we used to have to draw these things with pencils, right? And if you have to draw it with pencils, this isn't a bad approach, but there's really, as long as we have access to AutoCAD or something else, there's really not much call for drawing these things manually, certainly not drawing all the lines that step 7 is representing, right? It's just a much more efficient way to do that we're going to talk about in class. Regardless of the drawing method though, once it's drawn, we're going to have to go ahead and throw on some annotations, and that's what this slide is talking about, various dimensions that are important. And then of course, the notes calling out the individual components and exactly what they are. The open stair layout, as mentioned previously, is a run of stairs that basically has no riser boards. Now this is a fairly exotic example of that, but in all cases, the space between the treads is left open, and it just provides a little bit more open feel through this traversing these stairs. A side note here related to code considerations with open stairways like this, we need to make sure that that gap doesn't exceed the maximum gap size for any stair, and that would be between balusters, between treads, all of that. We just need to make sure that a baby can't get their head between there or a small pet even, and fall through. Again, a good drawing method for drawing this with a pencil and a T-square and a triangle is laid out for you, but we're going to talk about how to do it in AutoCAD in class. Okay, a U-shaped stair, and again, that's the shape of the stair looking at it in plan view. So you're going to go up one, run, hit a landing, you're going to spin around 180 degrees and continue up the other run to the next floor. In most cases, we're going to show a U-shaped stair by cutting the section through, in this case, the lower portion, and aiming our section view toward the upper portion, which we're going to draw either in projection or as a hidden line type of a drawing behind a wall. An L-shaped stair, on the other hand, isn't quite that easy to draw. As you can imagine, an L-shaped stair doesn't have a convenient spot where the next run is going to be easily seen. So what happens with an L-shaped stair is it'd be similar to this, but you'd go up one set of stairs, hit a landing, and either turn right or left. And then you would see all of those stairs just sort of as horizontal lines in projection. So what we typically end up having to do is actually create 2 stair sections, one through each run. So here's that view of what it would typically look like. So we would cut a section, in this case, through the bottom, and we're seeing the upper portion in projection. We're seeing the lower portion in section. We could also then cut a section through the top running north and south and look at that from either direction, just so we see the whole structure and how it's supposed to tie together. There are also different tread options that we have. So now we're looking at the stairs in plan view. The first one we're showing here is the winder treads, and actually option A here is no longer permitted by code. They've gotten away from this because of how quickly it drops in close to the corner. You can imagine slipping right here and falling 3 stairs. That's an ankle breaker. So what they've done instead is they've modified it to look more like B or C, to where we're pulling that last tread away from the corner, creating a minimum tread depth at the wall there at the corner. And you can see that depicted over here. So 2 things are going on in C that are describing what code requires. One is that minimum tread depth, which is 6 inches at the wall. And then the other one is the minimum tread depth at a point 12 inches away from the wall. In that case, it's 10 inches. Unfortunately, this requirement, although it's safer and that's good, it does sort of eliminate the benefits of having winder treads, which is adding an extra tread or 2 around the corner as opposed to just a flat square landing. Unfortunately, it doesn't really gain you much because of how far back we have to pull away from that corner with the last tread. So the winding stairs, as mentioned, incorporates into an L-shaped or a U-shaped design, and it just basically replaces the landing with steps. Again, the cost of doing that really doesn't pay off anymore with the new code requirements. Circular stairs, as you can see in the example here, this is a pretty fancy one, are going to typically be left open so that they create a focal point. There's not really any advantage to a circular stair as opposed to a straight or an L-shaped or a U-shaped. It's just an architectural feature. So curving architecture oftentimes is considered more appealing. Obviously, there's going to be a considerable cost involved as compared to a conventional stair if you do one like this. And that would mostly be because of the complexity of the construction, but also oftentimes the finished materials we have to use on a stair that's going to be left open and visible all the time. Spiral stairs are legal. We can create spiral stairs that are code compliant. And in fact, code has a special section in it that talks about what the different requirements are for spiral stairs as opposed to standard stairs. There are some advantages and disadvantages of spiral stairs. The main advantage is the very, very small footprint that they take up on the floor plan. You can imagine any other stair type to get from one level to the next is going to require a great deal more of the floor space than a spiral stair would. The disadvantages are probably obvious, one of them being how are you going to haul a bed or a large piece of furniture up those stairs? So we typically are not going to consider those a primary stairway. It might be a convenient stairway or a second stairway, or possibly just a stairway going up into a loft that has another means to get furniture up there. We started our discussion looking at a stair opening in 3D using SketchUp, and this is just another way to kind of discuss how we create that opening. On a typical floor, our floor members are going to run parallel to one another at a certain distance on center, but to get a stairway through a floor, we have to stop some of those, in this case, trusses from passing all the way through. So to do that, we double up the members on either side of the stairway so that they can hold a little bit more weight, and then we run headers across to support those members that would have otherwise passed through that opening. Typically, if it is a truss, the truss designer is going to build into the trusses a means for that lateral support going across those main support members. Here are a couple other examples. These are showing more related to conventional lumber, but you can see how all of the members around the opening, this is a pretty small stair opening, right? But all of the members around the perimeter of it are doubled up. We also have stairs on the exterior of our building, and oftentimes those are going to be used using some type of a weather-resistant type of wood, or in some cases, concrete. Generally speaking, if it's a stair that's right on the ground, we're going to be using concrete for that. And typically if it's a stair that's going up to a deck where there's air under it, typically we're going to be using wood for that. When I say wood, obviously that is going to include some other materials that are wood products. And we have a number of sort of wood and plastic combination type of products that are sold as being, more weather resistant and longer lasting. They don't rot, things like that. So that does conclude our discussion over Chapter 39. Please go out and take a look at the quiz and get that done at your earliest convenience. And we will continue our discussion. There's a lot more to say about stairs the next time we meet in class.